Hello everyone, we are Group 5 and our topic is margin and maximum margin principle. This table is a list of all members' contributions
that measures the minimum gap between the decision boundary and the nearest data point. This concept is important because it helps reduce model complexity. If the margin is very small, the model can easily be affected by noise, then leading to overfitting. And if the margin is large, the model becomes more stable and less likely to change due to small fluctuations in the data. So the idea of maximizing margin is similar to L1 and L2 regularization. Both aim to control model complexity and reduce overfitting, but in different ways. Regularization constrains the model by penalizing element size, while maximum margin constrains the model through its geometric structure.
I'd like to explain why maximizing the margin improves generalization in support vector machines. In SVM, the margin is the distance between the decision boundary and the closest training samples. When we maximize this margin, we create a classifier that is much more robust. New data points can shift slightly due to noise, but if the margin is large, they are still likely to fail on the correct side of the boundary. Second, maximize the margin helps reduce overfitting. A small margin forces the model to bend tightly along training samples, capturing noise instead of true pattern. Third, as we realize on a few key points called support vectors, by maximizing the margins around these points, the decision boundary becomes more stable and less sensitive to detect the composition of the training data. Finally, this idea borrows from structural risk minimization principle from statistical learning theory. As we minimize a combination of empirical risk and model complexity. That's why SVMs often perform well, even with limited data.
The right figure is large margin classifier. The decision boundary is placed around a feature value of 7. Its boundary correctly classifies all training samples. The key difference lies in the fact that its boundary is far from data points. On both sides, the marked margin is very wide. The model appears very confident and stable. It creates a wide safety buffer. Only new data points with feature values very close to 7 might be in an uncertain state, and this range is much larger than in the left figure. This corresponds to a simple, robust model. It gains stronger generalization ability for unknown data. It doesn't care about data points far from the boundary, only focusing on the most critical support vectors. This example perfectly illustrates the core idea of the maximum margin principle to find a decision boundary that not only correctly classifies data but also maximizes its distance from the closest data points for any class.